These eggs originate in industrial laying farms, where scale and consistency matter more than individual handling.
Eggs are laid directly onto conveyors within minutes. Speed reduces exposure time, but the shell is all clinches. Once collected, eggs move immediately away from the hens. Delays here increase microbial pressure on salad pores. Shells are naturally dirty at this stage. Aggressive cleaning here would be dangerous, forcing backs prioritize volume and consistency. Every egg is treated as part of a much larger biological system. Eggs are grouped in bulk trays. At this point, one compromised shell is already a shared risk. This scale is what defines industrial egg processing. Small failures here multiply quickly downstream. Before transport, eggs are stabilized. This step prepares them for movement without increasing contamination risk. Only dry debris is removed. Moisture at this stage would pull bacteria into the shell, creating irreversible.
Cooling slows microbial growth. Temperature control here reduces biological activity without damaging shell integrity.
Temperature is constantly monitored. Small deviations can create condensation later during transport. Shells must remain intact. Cracks formed here may not be visible, but they cannot be fixed. Eggs are stacked for transport. At this scale, individual inspection is no longer possible. Once sealed, responsibility shifts from the farm to the cold chain. Any failure now travels with the product.
Transport introduces new risks. Temperature stability becomes the primary defense against bacterial growth.
Eggs are moved in bulk. A single cracked shell now shares space with tens of thousands of others. Temperature control systems must hold steady. Fluctuations create condensation, and condensation carries back. Dry shells indicate success. Moisture here would mean silent contamination already in progress. Cold air circulates continuously. Transport is not passive, it is an active preservation step. Even airflow matters. Dead zones allow temperature pockets where bacteria can recover.
Once in transit, errors cannot be corrected. The eggs arrive either protected or already compromised.
This is where biological risk meets industrial control. From here on, hygiene becomes absolute. Eggs enter the factory without human contact. Automation limits exposure, but cannot eliminate risk. Tikia. Every movement is controlled. Precision reduces damage that could compromise shells. Equipment is continuously sanitized. Residue buildup would become a bacterial breeding ground. From this point forward, eggs are treated as exposed biological material, even before they are opened. Human contact is minimized. People introduce variability that machines are designed to avoid. Once sealed inside the process, every mistake ahead will scale rapidly, and none can be undone.
Washing is the first irreversible factory step. Done incorrectly, bacteria are pushed inside the shell instead of removed.
Wash water must be warmer than the egg. Cold water would pull contaminants through shell pores. Temperature is tightly controlled. Even small deviations permanently compromise shell safety. The mechanical action removes debris. Excess force creates micro cracks that cannot be repaired.
Sanitizers reduce surface bacteria. Overuse weakens shells. Underuse allows pathogens to survive. Eggs must exit clean and dry. Moisture at this point is already dangerous.
This process defines whether the egg is safe to open later, or already lost.
After washing, shells are inspected. Cracks invisible to humans are now critical threats. Machines detect structural weakness before breaking begins. This decision cannot be delayed. Microfractures allow bacteria direct access to the interior. No later step can correct this. One rejected egg protects thousands. Allowing it forward would contaminate entire batches. Rejection is expected. Yield is sacrificed to preserve safety.
These eggs are cleared to be opened. This clearance cannot be reversed. Only structurally sound eggs are allowed to move forward. The rest are already failures.
This is the final moment the shell provides protection.
Breaking happens in milliseconds. Any misalignment creates shell fragments.
Clean separation prevents shell contamination. There is no filtration safety net later. The egg is now fully exposed. Contamination spreads instantly from this point.
Shells are removed immediately. Contact with liquid is no longer acceptable. Liquid egg is biologically active and unstable. Exposure time is minimized. This line multiplies risk at industrial scale. Immediately after breaking, liquid egg is enclosed. Exposure time here must be nearly zero. This valve determines the egg's path. A wrong decision here cannot be corrected later. Whole egg remains chemically complete. Its quality now depends entirely on upstream hygiene. Eggs routed for separation enter a more sensitive phase. Precision becomes mandatory. Multiple streams run simultaneously. Cross-contact at this point ruins entire batches. Seals protect against air and microbes. Even microscopic leaks are unacceptable. From here on, whole egg, yolk, and white are treated as separate products. Separation begins immediately. Delay increases mixing and loss. Centrifugal force separates yolk from white by density, not color. Yolk contains fats and emulsifiers. Its contamination affects stability and flavor. Egg white is unforgiving. Even trace yolk destroys its foaming ability.
Separation speed is constantly corrected. Small errors escalate in seconds.
This boundary confirms success. Once lost, it cannot be recovered.
From this point forward, open air is forbidden.
Weld quality determines whether bacteria can hide permanently. Air bubbles signal oxygen intrusion. Oxidation begins immediately. Pipelines are cleaned without opening them. Manual access is too risky. Pumps move liquid gently. Mechanical stress damages proteins.
Oxygen exclusion preserves freshness and shelf life. Pasteurization begins here. Liquid egg must be made safe without destroying its proteins.
Heat is transferred indirectly. Direct heat would instantly coagulate the egg. The safe temperature window is narrow. Below it, pathogens survive. Above it, proteins are perlix. Time and temperature work together. Neither can compensate for the other. Flow speed defines exposure time. Seconds matter, and mistakes cannot be undone. Successful pasteurization leaves no visible sign. Failure often looks identical at first. This is the most unforgiving step in liquid egg production.
Once heated, liquid egg must be cooled immediately. Warm egg is unstable.
Cooling must be fast but controlled. Thermal shock damages proteins.
This cooling curve is engineered. Deviations allow surviving bacteria to multiply.
Cooling happens in stages. Stability matters more than raw speed.
At this point, the egg is safe, but only temporarily.
Holding tanks slow time. They do not forgive temperature abuse. From here forward, cold control is the only thing preventing failure from returning.
Quality control does not happen at the end. Samples are pulled while the process is still active.
Samples are sealed immediately. Exposure here would invalidate the results. These tests look for contamination that cannot be seen, smelled, or tasted. Viscosity reveals thermal damage. Overheated eggs fail here, even if they appear normal. Color shifts signal separation or protein breakdown. These changes cannot be corrected. Tested samples are destroyed. Nothing re-enters the system once removed.
This data decides everything. Entire batches are released or permanently rejected.
Packaging begins under sterile conditions. From this point, contamination must be prevented, not corrected. Air exposure is minimized. Oxygen shortens shelf life and accelerates spoilage. Fill accuracy matters. Underfilling introduces air. Overfilling compromises seals. Seals are formed under controlled pressure. A weak seal fails silently later.
This seal is the product's final defense. Once it fails, nothing can stop spoilage. From here on, the egg is passive. It can only be protected or damaged.
This line locks in every decision made before it. Finished product immediately enters cold storage. Temperature control becomes the final safeguard.
Stacking protects packaging integrity. Pressure damage can compromise seals. Temperature is tracked continuously. Short deviations leave no visible trace. Airflow prevents warm zones. Uneven cooling allows bacteria to recover. Cold stresses packaging materials. Weak seals reveal themselves too late. Distribution restarts risk. Every transfer is another test of control.
Once shipped, the factory's influence ends. Any failure now appears far from its cause.